Good morning or good evening or good afternoon, wherever you are. We're going to talk a little bit about GNU Radio now, and specifically about removing SWIG. So I'm Martin. I work for Edis Research on NI, and with me is Josh.
Hey guys, I'm Josh. I work with Perspective Labs in New Jersey, USA.
Right. Yeah, we're going to talk about Python and GNU Radio and all those things. Let's head straight into it. So our talk is split into two sections, basically. The first one is kind of the motivation for why we're doing all of this, and we'll also say what this is, in fact. And then the second half, more of like the second 2/3 of the talk, is about the actual implementation, what it looks like, and things like that. And I'm going to do the first part, and then Josh is going to do the second part. I'm going to head straight into it. So the why and the what of PyBind. So what's going on here? So we removed SWIG. Now, we're going to talk a little bit more about what that does in this talk, but like in a nutshell, SWIG is the thing that exposes the C++ code from GNU Radio into Python land. So we can actually write flow graphs or applications in Python. And for example, GRC makes a very heavy use of that. Now, SWIG has always been there since, I don't know, as long as I can remember. It's been a big and important dependency of GNU Radio, and it's like pretty ingrained. So why would we possibly remove it? That seems like a crazy thing to do, like a very invasive change. And these are often considered unnecessary. And I want to make very clear that we didn't do this lightly. We thought about this very carefully. And specifically, the way that we reached the conclusion that we want to remove it was thus. So first of all, anything that's a dependency of GNU Radio is something we review regularly. So we have a bunch of dependencies, like we require specific compiler versions, we require a specific version of Boost, and we have other dependencies that matter. And we always look at them because dependencies are always a liability. We always want to make sure that they're not dragging us down, or if we can remove them, or if we can replace them with something that's better. And SWIG was one of the most invasive and problematic dependencies. And that's because SWIG is very complex. Now, it's a very capable tool, and like kudos to the developers of SWIG. They've created something that does something extraordinarily difficult, but it is also very difficult to use. And for the day-to-day usage of GNU Radio, that might not be an issue. Like, people might not notice this if all they do is maintain an out-of-tree module. But we as the maintainers often had trouble keeping SWIG up to date. Whenever there's an actual bug, it's a big deal. And SWIG itself is a big deal itself. It's huge. And the compilation of all the SWIG code is massive. And one of the problems is that recompiling also takes a lot of time. So if you change a single file into your blocks, for example, and then you have to recompile it, it just takes an unnecessary amount of time. And SWIG is okay when it comes to all the standard blocks, but whenever you get out of the comfort zone of SWIG and you do something that we can't handle with our standard macros, like, it was extremely painful. You had to learn SWIG, and I already mentioned that was difficult. And finally, SWIG was chosen at a time when the GNU Radio community hadn't sort of fully committed to Python. So now that we have, and we're not going to start supporting other languages wrapped straight from C++, we know that we can also use a different tool. So SWIGHEL is what we meant, was what I mentioned earlier. It's what we named the place you end up when you actually have to debug SWIG, because you always end up with crazy compiler errors. And whenever I fixed them, I always felt like I had no idea how, or like I just did not understand it. So how did we actually reach the conclusion? What was the process? Like, big changes like these, we don't just drop them onto the code base. In fact, this started almost 2 years ago with a grep. The greps are our usual way of suggesting or introducing big changes. This is grep number 15, which is originally called Replace SWIG with something else, and posted by myself, really as a suggestion. Like, it didn't have a lot of content at the time. But we do take our greps seriously, or at least we try to. So we looked around, and we did find that PyBind 11 was a suitable tool. And Josh, who will talk about all the details later, actually volunteered to take over the lead of this really massive change. And took a while to get there. We had some experimentation and research to be done. We first published a branch called PyBind, quite simply, was published this year. And eventually Marcus, who's the maintainer of GNU Radio, decided it's time to merge it into master, even if it's not perfect, just so we give it some exposure. And then, of course, he announced it. And now if you're running master, you're already running PyBind. Why did we choose PyBind? Well, there's a bunch of tools that wrap C++, into Python. But if you sort of compare the available tools with the matrix of requirements that we have, it already drops down to a small number of useful wrappers, which makes sense because like you wouldn't have several tools all solving the same problem. Another tool that we looked at was Boost Python, but Boost Python is really just PyBind 11, but much worse. Another thought that we had was, well, maybe we just don't use an interface generator because we only have Python 3 now, and maybe we can just like straight up write C, but that was just too complicated. People from the community already had some PyBind 11 experience, and it, like, as projects go, it also is like, seemed best maintained and active, etc. And finally, PyBind 11 is easy to learn. It is really truly easy to learn. If you know C++, it's not at all difficult, unlike SWIG. Still a bunch of pros and cons here to consider. So with the change from SWIG to PyBind, you'll see later why, but we have a little bit more static code in our tree, whereas SWIG would generate everything at configure and make time. PyBind 11 does not. So that's both an advantage and disadvantage because there's a bit more manual intervention involved. But on the other hand, you don't have to recompile everything from scratch. So another advantage is that you don't have to learn SWIG, and you have to learn PyBind 11, already mentioned. It's much easier, and it's just C++ 11 with, like, you just look up a reference manual. Exposing types into Python is handled by PyBind. I already mentioned the compiles are faster. This is not necessarily a huge difference on the initial compile, but on recompiles, definitely. If you have lots of cores, like, you can use them more effectively. If you get something wrong, PyBind 11 will tell you. These are all really good advantages. I already mentioned, like, on the downsides, that there's a little bit more manual work involved. And there's like a couple of aspects to that. First of all, we had to write a bunch of new tools. They're probably buggy, and also they're not quite as evolved as what we had before. And if you maintain an out-of-tree module, well, you're going to have to port it from 3.8 to 3.9 now. All right, I'm going to hand it over to the guy who did most of the work here, Josh.
All right, so thanks, Martin. So now we want to know, okay, now all of your out-of-tree modules are broken. So how do I get to this PyBind 11 from all my SWIG wrappings, and how do I port to the new version of everything? So first of all, there's some new dependencies. So PyBind 11, we settled on version 2.4.3 or later, because that's what's shipped right now with Ubuntu 20 and the latest Fedora and CentOS. And then, so that's an actual dependency. That is what replaces SWIG. So there's another optional dependency, PyGCC XML, and this is used to automatically take your header file and put it into a format that can be used to automatically generate the C++ code that's used for the Python bindings. So this is not, it's not something that you necessarily have to use in your out-of-tree module. For very basic stuff, we have some pattern searching, the same things that were used in ModTool for creating the XML YAML files in the past. But we'll talk about that more as we go along. So the structure, the directory structure here. So first of all, the SWIG directory is gone, no longer needed. Now there's, in the actual Python directory, it's funny, there's going to be C++ code that lives in the Python directory, but it seemed to make the most sense for now all the Python bindings to live in the Python directory of the module. So if you look at, each block is going to have its own C++ file, its own compilation unit where the classes, the methods, enums, public variables are defined for that block. Everything that you do is there. And then there's one C++ file for the entire module that pulls all those together. Now, there's one other thing to consider here. There is, back in the SWIG days, there was some docstring scraping from the header files that was done a long time ago, and that's lived ever since. So we carried that forward, but it required a kind of a template, all of these, let's say, static variables that are a placeholder for the strings that are going to get scraped from the header files. So we'll talk about that more in a bit. All right, so now you want to create an out-of-tree module with GR 3.9 with these PyBind 11 bindings. So it's very straightforward. So the first few steps look exactly like out-of-tree modules did in the past. You create your out-of-tree module, new mod, go into that directory, add your blocks. And so then after you've added your block, go make your block do something. So now you're going to edit the public header file, you're going to edit the lib files, you can add all your signal processing. So now you're at a point you have a placeholder for Python bindings, but no Python bindings yet. So there's an additional function now in grmodtool. It's called grmodtool bind. And grmodtool bind is what is going to generate those. It's going to call PyGCC XML if you have it, or it's just going to use some Python code to automatically create the C++ code for your bindings. So let's take a look at the C++ code that's used for the bindings. So now you have myblock_python.cc. This is the per block, the per block bindings C++ code, and it's all pure C++ 11 code. You could write all this manually if you wanted to. It's very straightforward format, and it's straight from the PyBind 11 documentation. So the comment block, this is used in our CMake macros. There's a, I think PyBind 11.cmake or CMake files macro that does this. And so this comment block is used to detect whether your header file is in sync with the bindings. And the reason for that, what SWIG used to do, which was actually very nice, was it would take the header file, and every time you compile, it's going to regenerate all the bindings. Like Martin said before, now we're a bit more manual. There's more manual intervention. The bindings are more static, but we just wanted a way that we could say, hey, these bindings are out of date with the changes in your header file. So what we've done there is we've added a header file hash. And so it uses an MD5 sum on the header file, puts this in the bindings, and then it's easy for CMake then to detect whether you're out of sync. So the PyBind 11 includes a couple things to note here. These are the common ones: complex, STL. They're going to be used in most, if not all, out-of-tree modules. But PyBind 11 has more common bindings for common types, and they make it really easy to add in custom types into their bindings. So the public header file, that's expected. Your bindings link to that, and then the docstring. So this file, at the time you compile, this file doesn't exist yet. What you have in tree, you have a docstring template, and then at CMake time, your docstrings are going to be scraped, injected into that template, and placed into the build directory. And so this file actually lives in the build directory, and the CMake, links it to the build directory. And then here's the actual binding. So a couple things to note here. Actually, I think on the next slide, we'll talk about this in more detail, but this is, back to the comment header. Yeah, we can go back to the comment header. Sorry about that. Yeah, the big thing here is the header file hash. That we're trying to get to a point where this is all automated, which is why there's a couple other flags here about whether you want your bindings in tree to be overwritten automatically or not. That's kind of I don't want to say work in progress, but something that's a little more forward looking. The main things here are which header file to hash against and keeping that hash up to date. So again, these are a little more forward-looking, the other things in the comment block. So now back to the actual Python bindings. So take advantage of PyBind11's documentation. It's excellent. They talk about a lot of functionality that we're not utilizing in these, but you can, especially if you're using custom types. If you look at the first line, the bind complex. So this file, it's binding your block into the entire module. So it takes the reference to the module in, and it's going to add your block's bindings into that module. So this quirk right here, when we're defining the class that we're binding, the base classes have to be explicitly stated here. I don't know if this is a bug in PyBind11 or just the way it works. But if you look at this whole thing, it looks very boilerplate. It's something that, there's always room for improvement. This could be done with a macro probably. But for right now, this is the structure.
And, let me just add there, like, when you say this could be done with a macro, like that's something where we could, where we're always looking for volunteers to help simplify the process, because, the SWIG started out the same way where it was really awkward, and then it got simplified by macros, etc. So we're hoping to do the same. And if you want to help us do that, that would be great.
Absolutely. Help is always desired. The doc strings. So this macro, this is a PyBind11 macro that it takes the name of your block and references the docstring template file with a very specifically named variable, and then it's going to insert the doc strings into the Python bindings. Now, if you don't want doc strings in your Python bindings, or you don't care about them, if you just compile your out-of-tree module with Doxygen not enabled. So if you don't enable Doxygen, it's just going to copy the empty templates into your build directory, and then you're just going to have empty doc strings. So that's fine if you don't care about doc strings. If you have default values on your variables for any function you're exposing to the Python API here, you have to explicitly set the default values here. So our automatic tools will get those from the header file. If you have some argument equals some value, that will get parsed out by PyGCC XML and placed here if you're using those automated tools. But if you're doing this manually, if you want default values, you got to put them here. And one other nice thing about PyBind11 is that it allows you to put a custom function in as the constructor. So the init function in Python can map to any function in your block. In our, the structure of most blocks have this make function because we hide the private constructor in the implementation classes. So it's SWIG. Our SWIG files had something similar based on a macro. So there's nothing really that different here. So the PyDoc template. So there's a file. You see these variables are named very specifically. Again, if you're using automated tools, these get generated in the way they're supposed to. And then the scraping happens at CBank time, and a file gets generated with the actual doc strings in between these little tags here. So now you have a working out-of-tree module in 3.7 or 3.8. So how do you get to 3.9? Well, it's not bad. And actually getting from 3.8 to 3.9 is easier than getting from 3.7 to 3.8. So there were some very pervasive changes from 3.7 to 3.8. And the easiest way to get to 3.7 to 3.8, just generate a new out-of-tree module in 3.8 and work from there and copy your code in. Now, if you're going from 3.8 to 3.9, you can stick with your existing out-of-tree module, create a blank one using the 3.9 GR module, and then copy things back into your working out-of-tree module. And there's probably room for improvement here with more automated tools. Again, if folks have ideas, please share. And if you have time to work on them, these would be great improvements to the overall process. So just a little more specifically on getting from 3.8 to 3.9, use the 3.9 mod tool to create an empty out-of-tree module. And then in your working out-of-tree module, copy in the Python bindings directory, and then do a couple other small little mods, and you should be good at that point. So in tree, we always want to take a bit more care when we're modifying the in-tree code. There are some convenient scripts. So with grmod tool, it's going to modify your files in your tree. So again, be careful there. It's very similar to the way that if you say grmod tool make YAML, and then it creates your GRC bindings, it's very similar to that. But for in-tree, we don't have mod tool. So there's some other convenient scripts, and there's been some growing pains there with folks that have used them, Martin being one of them. And so if what these scripts do is they're going to create your bindings directory somewhere else that you specify. And they also require that the source tree location be specified and the prefix specified. So take a look at these scripts if you're modifying in-tree files. Python only flow graphs. So obviously these relied heavily on SWIG because that was the main binding mechanism. With PyBind 11, this implementation actually became much more straightforward. We don't gain any performance enhancement, which, unfortunately, you're not going to be able to write Python only flow graphs and have them work as well as C++ ones do. But there is a benefit here that the original SWIG director-based functionality, it had a fairly complicated message passing interface to get the whatever you were doing between Python and C++ communicated back and forth. With PyBind 11, they have interpreter embedding, and so it makes it very straightforward to say now call the work function on the Python, and we get all the base blocks for free, all the base block methods, I should say.
I just want to say that Python performance was actually never that bad. It's just a bit slower than C++. But if the combination of NumPy and that C++ schedule, they give you pretty good performance even in Python.
Okay. So now, of course, this isn't all new. So there's things that we're going to run into, and just want to highlight a few of them so that there's no big surprises here. If you have blocks that use C++ templates to, to have different typed interfaces. So say you have an add block, and your add block uses standard templates to wrap it, and then you have a float version, a complex version, a uint8 version. This is not going to work great with PyGCC XML specifically. What happens right now, the bindings come out empty. So if you have templated blocks, you're probably going to have to write the PyBind 11 bindings manually or copy it from somewhere else and edit it. Doc strings, currently in the CMake file, if you're doing incremental compiles, you can get into this. The CMake has written the doc strings, you change something, so the doc strings are out of date. So it's easy to get out of that state by either making clean or removing this docstring status output. But there's room for improvement here in the CMake. And I guess the other one I want to highlight here is using external libraries. So some modules, GRQT GUI, and any out-of-tree modules that are based on GRQT GUI, they reference external libraries. And the way PyGCC XML works is it does a compilation of the header file against whatever external libraries that are referenced there. And so it needs to be able to find those, compile against them, and the convenient scripts have a placeholder for additional include directories to be specified. So take a look at the notes in bind gr module. So it has specific notes for UHD and Qt GUI, but you probably find something similar if you're referencing other external libraries in your out of tree module. All right, so where do we go from here? Our goal is for this to be fully automated and as smooth as a workflow as using SWIG was, without all the downsides of SWIG. Right now, there are a couple quirks. We want to work those out, but we want to get to the point where, you have your header file. You can either CMake or compile. All the bindings are generated automatically, except where you don't want them to be generated automatically. And what's in the way right here of doing this is, the limitation we mentioned before, and PyGCC XML is fairly slow. So, this is our call for help right here. If you're interested in helping to make the workflow smoother and automating this, and you have ideas, speak up, jump in. The help is always wanted on this. PyGCC XML, we're using it to do the lexical parsing of the header files. And so it takes the header file and it generates some objects that we then make into a JSON file, use the JSON file to create the PyBind 11 code. There's other tools that we could use to do that, or, some kind of regex parsing, which we use for the basic stuff. So if we could expand our abilities with the regex parsing, or use some other tool that's quicker, that would be a big win for PyBind 11 in the loop here. So a couple things to take a look at for further reading. One, there's 3.9 out of tree module porting guide that has more information on the whole process and the pieces of PyBind and other things that are going to impact you. And then also the PyBind 11 documentation. Again, it's very well written, and you can get an idea for some of the other functionality of PyBind 11 as well.
Yeah, I think that wraps it up, right, Josh?
Yeah, I think so.
Thanks to you, Josh, for doing all the hard work on this.
And thank you, Martin.
Yeah, you're welcome. But I was also going to thank everyone who participated in testing and, had comments. And, I'm going to proactively thank anyone who helps us with future testing and finding issues and making it easier. Anything else, Josh?
Cool. That's all I've got. And I think we're at our time limit here.
Okay. Well, have fun with new PyBind 11, and bye-bye, everyone.
Thanks, everyone.